Hello, everyone. My name is Justin. I'm the machine learning for IoT group, also called as Maestro. My advisors are Shantanu and Professor Ortiz. This is a normal weekday 9 a.m. to 10 a.m. occupancy distribution graph of a high school. As you can see, the red dots represent the students who are currently in class, and the auditorium and music drawing room are currently empty. These four green circles represent the fire exits. In case of emergency, students on the left wing, they can exit the building via the left fire emergency escape. The students in the mid wing, they can exit the building via the auditorium fire escape. And the students on the right wing, they can exit the building via the right fire escape. But let's take another step. Let's take a step back and consider another case of scenario where a school assembly is in session. All of the students are in auditorium, and the only accessible fire escapes are the ones inside the auditorium. So the distribution of each fire escape changes significantly, but the static evacuation routes remains unchanged. So is there a way that we can take advantage of that? As you can see, the corridor is currently empty and no one is using it. A more efficient evacuation route would be take advantage of that empty hallways. So can we build a system to solve that problem? Can we build a system that can tell us the current occupancy distribution? Can we build a system that measures the hallway capacity? Can we also build a system for quick information dissemination? Can we also build a system to tell us the location of emergency? For current occupancy distribution, here are some things that we should do to solve that. One of which is to do a deployment of non-intrusive sensors. That means we can deploy a number of sensors on the floor that can give us live feedback. And we also have to ensure the sensors readings are correct. And after we collect all those data, we should also send those data to a centralized hub for data analytics. For a capacity calculation, is there a way that we can measure the speed of human movements in the corridors during class, lunch hours, entrance and exit times? For information distribution, we also need to place lights on the hallway floors, or can we build a sensor system that can trigger the fire marshals when there's a case of emergency? And now please allow me to introduce you SmartBox and SmartDash. So as you can see on the left side, that's the prototype of our hardware SmartBox, and the right side, that's just the full stack framework. It's called SmartDash. Before we talk about the real world application, let's talk about the system design first. So as you can see on the left side, SmartBox is powered by Raspberry Pi 3, and the data collection is enabled through an Arduino Uno connected to various sensors, which I will go into details in a later slide. The SmartBox has one function: to collect data at 1 second time intervals and send them to the centralized database. A camera is also attached for users' convenience while labeling, so that a video feed can be shown during the active learning phase. A picture is taken from the camera every 2 seconds. The user can remotely turn the camera on and off by modifying the configuration file on the SmartBox. We intend for the camera to be turned off after the initial training phase, so as to minimize privacy concerns. Every 10 seconds, the SmartBox issue a post request in JSON with 180 total sensor readings. Timestamps are given as UTC timestamps rounded to the nearest second. After we update all those data to our MongoDB database, it acts as a medium between the SmartBox and SmartDash. So the SmartDash, the front end, so SmartDash is a full stack framework. After it allows users to select the specific data, and it will generate 18 parameter graphs based on users' input. And after we generate graphs, SmartDash also allows to ask users for certain labels. And for the future goal of this project, we also want to include a activity recognition machine learning classifier to achieve some interesting machine classifying task. Here are a list of data that we collect via our non-intrusive sensors. As you can see, there are two major components are left out, which is the camera feed and audio, and microphone. And we did that on purpose. The reason for that is because we want to classify this project as a non-intrusive sensors. And by including those two will definitely violate our, our goal. And this combination of sensors is also affordable, which means we can deploy them in a mass scale later on. Here's another look of our project. This is another look of how can we interact the front end with the database. As you can see on the right side, user can choose the specific box name they want to see, the start time, end time, and the channel names, and the front end will will generate 18 parameter graphs. And based on this 18 parameter graphs, users could also select segment of data, as you can as the red arrow pointed as such. It will allow user to manually update a label they're seeing they see is incorrect. And on the left side, you can see it works perfectly when we update the start time and end time, also with the custom label to our backend database. Some other real-world application of this project, one of which is to monitor daily activities. We can place Smartbox in home of elderly people that will allow us to monitor their life. We can also classify their behavior, such as using a microwave or vacuuming based on our future machine learning classifier. It's also good for a central heat system. The active learning can help us to understand occupancy schedules and comfort preference of occupants. This will also allow us to save energy by keeping the AC unit on and off based on the presence of our occupants. Here are some of the future goals. We want to deploy SmartDash publicly. We also want to simplify interface for multiple SmartBox connection, and we hope we can deploy those SmartBox on campus at some point. Thank you all very much.